Yeah, then go ahead. Let's get that cleared, then we shall get started. You can unmute and speak, or
Yeah, yeah. Oh, thanks. Actually, it was in week 10, lecture 3. So,
just
yeah, sure.
it's a different device that I'm using.
Okay.
What is this? Let me leave the call and come back. You see my screen?
Yeah, yeah.
Every session gives our doubts, and then there will be one extra session after this. So we after today we have got two more sessions left. One will be next week during week 11, and then another one week 13. That will be sort of a revision session. Okay. So Shivak, your question was week 10.
Lecture 3.
You can see the screen,
Yeah,
right?
yeah, sure. Next slide. Yeah, here, just here. Yeah. So here actually, last time you have told me that how that volume and this time integral has flipped. We have flipped, right? Right. After that, also we integrate in time.
Yeah.
So I understood that we have, if I take this flux term,
Hmm.
uh, so we take the average value of flux between this tn to tn plus 1.
Yeah, sort of a linear
So,
interpolation of it.
yeah, so it become a constant and comes out of integration, and dt become t, and we just put the limit, so we get this
Yeah,
term tn minus 1.
yeah,
Okay. Okay, so this term I understood, but the again the doubt comes in the temporal term,
hmm.
that there actually what he said, that dt get cancelled,
Hmm.
right?
Yeah.
Once dt get cancelled,
Hmm.
so what we are left with phi rho phi p del v is what we are left with.
D of rho phi p. I mean differential of rho phi p.
Yeah, that's what I don't understand, because it rho phi p are constant and del v
No,
is
no,
also
not
constant.
constant. That can be a function of time as well, right? And here, after you cancel out the two dt's, the limits of integration will also change. Like instead of going from tn to tn plus 1, it will go from phi pn to phi pn plus 1.
Okay. Maybe this is some very basic doubt of integration, but can you elaborate a little bit on this,
It's
because I don't
basically,
understand.
see, the thing is, phi p is a function of time. So time tn, phi p was phi pn, and at tn plus 1, it becomes phi pn plus 1. So
Yeah.
this is simply, so if you forget delta v for a second and also forget rho for a second, because these are all constants. So you're basically integrating the differential of phi p with respect to time. So you're basically integrating it over time, integrating phi p over time. That's what gives you this difference which comes out later, that 5pn plus 1 minus 5pn.
Yeah, now I understand because the average value of this 5p is also changing because
Yeah, yeah, we are not
5p
taking average here. We are taking the exact values at tn and at tn plus 1. Think of it
no no
this
no
way. So,
no, sorry, just a minute. This 5p we have discussed that it is it's the average value at cell center,
oh yeah,
but at
average
time
for
tn
yeah,
in this way it is also changing with time. Now I understand what you're trying to say, but then we like, is it just a notation? Why do we need to cancel it dt like?
yeah. That's just notation. I mean,
Yeah, it doesn't make any sense that
so
like.
basically, see, you're integrating dx dt dot dt with respect to integral dx dt into dt. So you're basically integrating dx.
Yeah, now, yeah, this is a very nice example.
Yeah,
If you go by this, now it is in easy to explain now. So if I just want to conceptualize this thing that if I am differentiating x with respect to t, and then I am again integrating it with respect to t, eventually I'm what I'm going to get is x,
yeah,
right? So
exactly.
here, that's my question here. Now x here is also maybe a function of time, and it is rho phi p del v.
Hmm,
But phi p, let's say, forget some time for rho and del v,
hmm,
just take phi p.
hmm.
Now phi p, we have d phi p upon dt into dt. Let's
Yeah,
say this is what we have.
yeah.
Now phi p is a function of time,
Hmm,
but I differentiate it with respect to time and we integrate it with respect to time,
hmm.
then I like eventually get what is phi p.
Yeah.
Why? Yeah. So now,
Why the
why we
difference?
need to? Yeah. Why the need of limit?
Because it is a what do we call it? Finite integration, right? What's the name? I forgot. So there are two kinds of integration, right? One is without limits and one is with limits. So this is
Yeah.
a limit
Indefinite
one.
and definite integrals.
Yeah, that's why you get the difference.
No, no.
Because
That's I understand it.
yeah, definite
Yeah.
and indefinite integral. Since this is a definite integral, that's why you get the difference of phi p between 2 points and not some phi p itself.
No, that's okay. But instead, still, I don't understand because why actually, if we don't, like, what I get is finally x. So I don't need to put even the limits.
No, you get x1, x2 minus x. Okay, let me do the maths.
Yeah.
Is my screen visible?
Yes.
So stop sharing this file. So see, simply this is what is happening. So one, two, you have dx dt. You're integrating it with respect to time. You cancel these two out, you get dx. Now the limits of integration will now change from time. So it will become whatever x was there at 1 and whatever x will be there at t. Let's call these x1 and x2. So this integration simply gives you x with the limits x1 and x2. So finally you get x2 minus x1.
Yeah, this I understand.
Hmm.
But what I am asking is a little philosophical way
Okay.
that, yeah, that if I am integrating x with respect to t
Hmm.
and then I'm integrating it with respect to t,
Hmm.
then it eventually gives me only x. Where is the need to put the limits?
No, because see, you initially start out with this, right? This is what we are trying to evaluate, and that gives us a definite integral of x.
Okay.
Definite
Can you
integral of
go?
dx. Sorry.
Okay, so instead of canceling it dt dt, can you go without canceling it? Like, finally, we have to get that only.
Yeah, see, okay. So we will mark this as of. This is the function we are trying to integrate with respect to. So
Yeah.
see the integration of dx/dt with respect to time itself is x. That's what you get. And these are limits.
No. Uh, well, uh,
So let's take
no
some. So let's
differentiation.
say if you had the double derivative, okay, that the double derivative of x when you're integrating, what will you get? You'll get dx dt, and
Yeah.
this will go from t1 to t2. So whatever dx dt was there at t1, whatever dx dt will be there to the next. Here the integration of dx dt with respect to time is x. See, this is
Integration.
calculus.
Yeah.
You should know
Yeah, yeah, yeah,
this.
I know it is calculus. Yeah, I know it is calculus, but it's a very old doubt. So I just want to discuss it. So actually, differentiating this will give x only with respect to time.
Hmm. Yeah, that's
It
what
will
you
not
need
change.
because it is a definite integral. That's why you have to take the difference, the limits.
Okay. Yeah, it may be some
See,
fundamental. Yeah, yeah,
let's say this is your x-axis. So this is x and this is time. What you're trying to evaluate is the difference at these two points. So, or rather, this thing. This might make it. So integration of anything can be thought of as area under the curve, right?
yeah,
So here we're trying to our function which is getting integrated integral is dx dt, and you're going from t1 to t2. This is the
yeah,
area that we're trying to evaluate.
yeah,
And you integrate this and you take an x. So this is the rate of change of x. So that you started out from some x and some. So let's say if this was constant, okay, then this will be a
yeah,
linear function. This will be linear
yeah.
with this difference x2 and x1. This difference will be equal to this area and this area.
This difference is equals to this area.
Yeah, because this is the integral of, think of it as velocity and distance. So this was your constant velocity. Whatever your distance increased between T1 and T2, that's equal to this area.
Yes.
That's the idea. That's how you get x2 minus x1 and x1. Does this make it clear?
It gave me an additional thought processor definitely, because this way I have not thought it. So I will might thought it and will let you know that if I get clear, because it take some time to digest this thing. Because like a variation of x with this is a very good like means explanation anyway. But like this area I need to like think that how it is equals to this x2 minus x1, because
See, you start out at T1, you have a
yeah,
velocity, some velocity. you
Yes, yes.
that velocity into the time difference. So what is this area? This area is this velocity, which is x1 x2 minus x1.
Yeah,
This is the distance covered, right? So x2 minus x1. The distance
yeah.
covered is equal to this.
Oh, wow. Yeah, yes, 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 yes. Yeah, now, yeah, it's a very nice explanation. You think it just right now, or like you already know this? Like, what is the approach to have this thought? That I also want to
See the
understand.
main
So, see
so the
about.
main funda is that integration is like area under the curve, and this I took constant so that you can understand it better.
Yeah, very nice. Thank you. Yeah, yeah, yeah. Thank you very much. And actually, today, like I need to leave, so that's why I asked you. I have collected some doubts, but those I think we can, if you allow, we can discuss in next session.
Sure.
Yeah. Okay. Okay. Thank you very much. Huh?
Okay.
Thank you.
So let's start with the questions of today's session. So question number one, we have for momentum conservation, the 2D steady convection diffusion equation is option A linear, option B nonlinear, option C insufficient information. Let's take a look at the answer. It is nonlinear because the convection term brings in the nonlinearity. Alright, now moving on to the next question, which is asking us select the correct statements related to the Scarborough criterion. This is something we learned in the third lecture. So this quantity R, which is equal to summation of the absolute values of A and B over the absolute value of AP, where we write our equation in this way that AP phi B is equal to summation of A n B phi n B plus some B, but that doesn't really, B doesn't really matter here. So what does Scarborough criterion say? Is it that uh, for convergence, does R have to be less than equal to 1 for all points, or is it? So there are four statements here. You have to pick out the correct one. So, or the correct combination. So in the options given here, there are combinations. So the statement 1 says that R has to be less than equal to 1 for all points. Statement 2 says R less than 1 for at least 1 point. Statement 3 says that R less than 1 for all points. And statement 4 says that R less than 1 for at least 1 point. And the combinations which we have in the options are option A, statement 1 and 4, option B, statement 2 and 3, option C, statements 1 and 2, and statement D, 3 and 4. Let's take a look at the solution. It's actually option 1, option A, that is 1 and 4. If we go back, so basically R has to be less than equal to or less than or equal to 1 for all points, and for at least 1 point it should be less than 1, not equal to, not just equal to, it should be less than 1 for at least 1 point. If more than 1 point, well and good, but yeah, for at least 1 point. If it's less than 1, then Scarborough criterion is satisfied. And Scarborough criterion tells us that if these matrices which we are solving using iterative methods, if they are diagonal dominant, then we can guarantee that it will converge. And diagonal dominance is you know mathematically quantized by this number, quantified by this number, sorry. All right, so moving on, we'll move on to question number 3 of today's session, which is asking us that for convection diffusion equations, what is done to ensure that Scarborough criterion is satisfied? Is it that option A, upwind scheme is employed? Option B, central difference scheme is employed? Option C, Crank-Nicolson scheme is employed? Or is it option D, none of the above? Let's take a look at the solution. It's actually option A, that the upwind scheme is employed. So we saw that using an upwind scheme basically guarantees that your uh, matrices become diagonal dominant. The coefficients A and B and AP become such a way that these diagonal dominance is ensured. Scarborough criterion is satisfied. Now, in case of central difference scheme, which we have seen that the cell Peclet number becomes important, and we can control the cell Peclet number by making the grid size smaller and smaller, so that Scarborough criterion can be satisfied. Now, that puts a condition, uh, you know, to be met from our end, but upwind scheme really relaxes that strong constraint. You can use a relatively bigger grid size, but that particular barrier is not there. Then again, your grid size will be determined by other constraints, but not this. All right. So moving on, we'll move on to question number 4, which is asking us that for first order upwind scheme, what is the most general way of estimating FE phi E? Is it option A, FE phi P? Is it option B, FE phi E? Is it option C, FE phi P minus FE phi E? Or is it option D, the maximum of Fe, 0 into phi p minus the maximum of minus Fe, 0 into phi e? The main keyword here, that what is the most general way of estimating by Fe phi e, and this is for first order upwind schemes. Okay, so let's take a look at the solution. It's actually option D. So the correct way of writing Fe phi E basically changes with the direction of Fe. So let's say if Fe is greater than 0, that is if flow is growing from left to right, U greater than 0. Then in this situation, the correct way to estimate Fe phi E is to take the upwind point, that is Fe phi P. And for the other scenario where u is less than 0 or Fe is less than 0 and your flow is going from right to left, in such a scenario, your upwind point is the one at the right. So you take Fe, phi, capital E. Now, here you see that there are two different values depending on the value of Fe. Now, one way to combine these two equations is to write this. So, where you take the maximum of Fe comma 0. So, if Fe is positive, this will be positive, and you'll get Fe into phi p. You'll get this first equation, and also this second term where you are taking the maximum of minus Fe and 0, then 0 would be the maximum between these two, and you will get 0 added to it. So basically it doesn't change, you'll only get this first term. Now in the other case where Fe is less than 0, then this first term, when Fe is negative, then 0 is the maximum between these two, and so this entire first term doesn't contribute, and it's only the second term that remains, where minus Fe, since Fe is negative, this is now bigger than 0, and you get minus minus plus Fe into phi e, which is this second equation. So in a more general way, you can write the value of Fe phi e in this way. So it really takes care of both scenarios. Okay. All right. So moving on, we'll move on to question number 5, which is asking us what is the order of accuracy of the quick scheme? Is it option A 1, option B 2, option C 3, or option D 4? A quick scheme is the abbreviation of quadratic upwind interpolation for convective kinetics. Quick, quick. This is a very popular method you'll find in many popular CFD solvers like ANSYS Fluent, COMSOL, and OpenFOAM, and so on. So the question is, what is the order of accuracy of this quick scheme? Is it 1, 2, 3, or 4? Let's take a look at the answer. It's actually 3, because we, so if we do the Taylor expansion, so let's say phi e is equals phi p plus phi p minus phi e divided by delta x by 2 into dou phi dou x at p, plus we'll have phi p minus phi e whole square divided by delta x by 2 squared, and also you have a 2 factorial here, and you have the second order derivative of p with respect to x again at point p, and you have other terms which are third order. So in the quick scheme, up to this is evaluated. We take central difference for finding out these uh, derivatives of phi with respect to x, that is dou phi dou x and dou 2 phi dou x2, and that's why this particular scheme is third order accurate. All right, so let's move on. We'll move on to question number 6, which is asking us that for u greater than 0, how is phi small e represented in the quick scheme? So there are 4 options given below. Pick out the correct one. Let's take a look at the solution. It's actually option A, that is 3/8 of phi E plus 3/4 of phi P minus 1/8 of phi W. So basically, if you go back here and you evaluate these differentials, so basically dou phi dou x, if you write it as phi P minus phi E, or sorry, by p minus by capital E divided by delta x, and for the second derivative you again use central difference, so you get at p, so basically phi e minus 2 phi p plus phi w divided by delta x squared, and you plug these in over here, then ultimately you will get as if you algebraically solve for phi e, you will recover this equation. All right, so moving on to question number 7, which is asking us which terms are absorbed into the flux term j vector while integrating the governing equations. Is it option A, the transient term and convection term? Is it option B, the convection term and diffusion term? Is it option C, the diffusion term and source term? Or is it option D, the convection term and source term? It's a very simple question. So the answer to it is option B, that is convection term and diffusion term, because these two are the terms which contribute to the transport of phi. So you have rho u into phi minus the gamma into grad phi, which is the diffusion term. So this is the convection term and this is the diffusion term. And these two are the ones which get absorbed into the flux term. This is again a vector. This grad phi is a vector. Alright, moving on to question number 8, which is asking us what is the correct expression for Cell-Peclet number? So Cell-Peclet number, as we saw, was the uh, convective coefficient f divided by the diffusion or diffusive coefficient d for a particular cell. So what is the correct expression for it? Is it rho u dx over gamma? Is it rho dx over u gamma? Is it rho u over gamma dx? Or is it u dx over rho gamma? So f, as we saw, was rho u a, and d was gamma over dx into a. So now if you simply do f over d, you get rho u a divided by gamma a by dx. So dx will go up, a and a will cancel out, so you should finally get rho u dx over gamma. So that should match with option A. Let's take a look at the solution. It is actually option A. So hope that's clear. We will keep moving along. We'll move on to question number 9, which is asking us which is the requirement for Cell-Peclet number so that Scarborough criterion is satisfied. This is for central reference schemes. Is it option A, Peclet number equals to? Is it option B, Peclet number less than 2? Option C, Peclet number greater than 2? Or is it option D, none of the above? Alright, let's take a look at the solution. It's actually option B, Peclet number less than 2. So this basically stems from, the terms like AE, where, you have FE minus DE over 2. Did I write that correctly? So basically, if your DE is, sorry. So basically, if your DE is greater than twice FE, or I'll just drop the E and write it this way. If this is greater than 2F, then this whole term might become negative, and in that case, sorry, I think I wrote this correctly initially. So if your F is greater than 2D, then it has a chance of becoming negative and ultimately breaking your Scarborough criterion down. So your sorry, what am I doing? So your F basically has to be less than 2D. So your F by D has to be less than 2. And F by D, as we know, is Peclet number. So this Peclet number has to be less than 2. This is so that AE is positive. Any neighbor or whatever. So for that to be positive, F has to be less than twice D, and F by D has to be therefore less than 2, and Peclet number has to be less than 2. Okay, so let's move on to the last question, which is asking us that at convergence, what is the value of the sum of the convective coefficients? That is F. Is it option A, summation FF is equal to 1? Is it option B, summation FF less than 1? Is it option C, summation FF greater than 1? Or is it option D, summation of FF equals 0? So summation of FF, as we saw, is basically FE minus FW plus FN minus FS. Now, the main point here is that at convergence, what is the summation of these? And you remember that these are convective coefficients. So this is rho UEAE minus rho UWAW plus rho UN an minus rho us as. What should be the condition of this particular summation? Should it be equal to 0? Should it be equal to 1? Should it be less than 1? Should it be greater than 1? Or should it be equal to 0? Okay, so let's take a look at the solution. It should be equal to 0 for simple reason that these are all fluxes coming in and going out. So the net summation is the net outflow. So basically this is what is going out, going out this way, and going out this way. So for an incompressible flow, this net outflow cannot have any non-zero value. It has to be zero. Whatever goes in, whatever comes in goes out. So this net flux has to be equal to zero. Now for compressible flows, this may not have to be true. There could be then again for steady compressible flow, it has to be zero because their rho is also a function of space and time. But for unsteady case, it doesn't have to be zero. It could be uh, non-zero. Like uh, for a compressible case, there can be accumulation and release of material of mass in any given control volume. Okay. Basically the not mass, the density can change. So flows can come in and increase the density within a particular control volume, and again flows can diverge out and reduce the density within a particular control volume. So in unsteady cases this is again possible, that this summation ff is not equal to zero. But for incompressible flows, both steady and unsteady, as well as compressible and steady flows, it will be equal to zero. Okay, that brings us to the end of today's session. Today was week 11. Now we will have another session next week, that is week 12, and then the immediate next day, if I'm not wrong, we will have week 13, which will be like a revision come doubt clearing class. Okay, all right. So thank you.